There exists a moment, perhaps you have experienced it, when you step outside on a clear night and gaze upward at the vast expanse of stars. The sky unfolds above you like an ancient tapestry woven with points of light, and in that moment, something fundamental shifts within your consciousness. You become aware, perhaps for the first time or perhaps again, that you are looking not merely upward but backward through time itself. The photons striking your eyes have journeyed for years, centuries, or even millennia. That star you see may have already perished, its light a ghost message from a long-extinguished sun. This is where our story begins, not with answers, but with the profound and humbling questions that have captivated human consciousness since our species first learned to wonder. The universe, in all its majesty and complexity, remains fundamentally mysterious to us. Despite tremendous advances in astronomy, physics, and cosmology over the past century, we find ourselves standing at the threshold of understanding, peering into an abyss that reveals new mysteries with each discovery we make. The mysteries of the universe are not failures of science. Rather, they represent the very edges of human knowledge, the frontiers where imagination, observation, and mathematics converge in an eternal dance of inquiry. As we embark on this journey together, we will explore some of the most profound enigmas that have captured the attention of scientists, philosophers, and dreamers alike. We will travel from the infinitesimal quantum realm to the cosmic expanses that dwarf comprehension, from the first moments after the Big Bang to the ultimate fate of existence itself. The physicist Carl Sagan once wrote that, "The universe is a pretty big place. If it's just us, seems like an awful waste of space." This sentiment encapsulates one of the deepest mysteries facing us. We do not yet understand our place in the cosmos, nor do we comprehend the true nature of the universe itself. Are we alone? What is the nature of consciousness in a universe governed by physical laws? What lies beyond the edge of what we can observe? These questions, and countless others, form the tapestry of cosmic mysteries that we will unravel in this exploration. Part 1, The Enigma of Dark Matter, the Invisible Scaffolding of Reality. The Discovery of Absence. Imagine you are watching a ballet performance. The dancers move across the stage with grace and precision, their movements following the music, the laws of motion, and the force of gravity. Now imagine that as you observe, you realize something profoundly disturbing: the movements of the dancers do not match what you see. They move as if invisible partners guide them, as if unseen hands direct their paths. Their trajectories suggest the presence of mass and force that you cannot perceive. This is precisely the situation astronomers found themselves in during the early 20th century when they began to notice that galaxies and clusters were moving in ways that violated the predictions of their calculations. In the 1930s, Fritz Zwicky, a Swiss astronomer working at the California Institute of Technology, made an observation that would fundamentally alter our understanding of the universe. He was studying the Coma Cluster, a collection of galaxies approximately 320 million light-years from Earth. By measuring the velocities of these galaxies using the Doppler effect, the same phenomenon that causes an ambulance siren to shift in pitch as it approaches and recedes, Zwicky calculated how much mass would be needed to hold this cluster together against the centrifugal force that should scatter it to the cosmic winds. What he discovered was startling: the galaxies were moving far too quickly. According to his calculations, they should have been flung apart long ago. Yet there they remained, held together by gravity. The only logical conclusion was inescapable: there must be significantly more mass in the cluster than what could be seen. Zwicky called this invisible substance dark matter, a term that would echo through the decades of cosmological research to come. For decades, Zwicky's discovery was largely overlooked or dismissed. Astronomers believed perhaps he had made an error in his calculations, or perhaps the cluster was simply in the process of dispersing. The scientific community was skeptical. It seemed almost unbelievable that the universe could contain vast quantities of matter that remained entirely invisible to our instruments. The visible universe, the stars, nebulae, planets, and gas clouds that we could detect through telescopes, seemed sufficient to explain the cosmos as we perceived it. The evidence accumulates. It was not until the 1970s that the mystery of dark matter returned to the forefront of astronomical research with renewed urgency and more compelling evidence. Vera Rubin, an American astronomer whose career was marked by both brilliant discoveries and discrimination within the male-dominated field of astronomy, conducted meticulous observations of galactic rotation curves. These curves map the velocity of stars and gas at different distances from the center of a galaxy. According to Newtonian mechanics and our understanding of gravity, stars near the outer edges of a galaxy should move more slowly than those closer to the center, just as planets in the outer solar system orbit more slowly than those near the Sun. Yet Rubin's observations revealed something unexpected: the rotation curves remained relatively flat. Stars at the outer edges moved nearly as fast as those closer to the galactic nucleus. This observation, replicated across numerous galaxies, suggested that each galaxy must be surrounded by an enormous halo of invisible matter extending far beyond the visible stars. The implications were staggering. If such observations were correct, then the visible matter, the stars, planets, nebulae, and all the luminous material we could see, constituted only a small fraction of the universe's total mass. Calculations suggested that dark matter comprised roughly 85% of all matter in the universe, leaving the familiar material made of atoms, the substance of which you and I and all visible objects are composed, as merely 15% of the material content of existence. Think of it this way: imagine you are observing a civilization, and you can only see 15% of its population. The other 85% remains completely invisible to your instruments, yet you can deduce their existence and even estimate their distribution and behavior through their gravitational effects on the visible population. This is precisely the situation astronomers face in studying the cosmos. We live in a universe dominated by matter we cannot see, whose nature remains one of the deepest mysteries in physics. The nature of the invisible. What is dark matter? This seemingly straightforward question has eluded definitive answers for over a century. Scientists have proposed numerous candidates, each with different properties and implications. Understanding the nature of dark matter requires us to venture into the realm of theoretical physics, where possibilities multiply and certainty becomes increasingly elusive. One prominent candidate for dark matter consists of particles called WIMPs, weakly interacting massive particles. These hypothetical particles would barely interact with ordinary matter at all, passing through the Earth, the Sun, and your body constantly without leaving a trace. Billions of WIMPs might be streaming through you at this very moment, and you would remain utterly unaware. Experiments like the Large Hadron Collider at CERN in Geneva and specialized dark matter detectors buried deep underground have searched for evidence of WIMPs, but so far, they have evaded capture. It is as if we are seeking to identify a species of animal that lives in our world but remains forever invisible and intangible to our senses. Another candidate, proposed by physicist Stephen Axion-Sicovy in 1983, involves axions, hypothetical elementary particles even smaller and lighter than WIMPs. These particles, if they exist, would be produced in the cores of stars and would pass through matter as effortlessly as neutrinos. The Axion Dark Matter Experiment, or ADMX, uses powerful magnetic fields to attempt to detect axions, converting them into detectable microwave radiation through quantum effects. The search continues, methodical and patient, in the tradition of experimental physics. More exotic candidates have been proposed as well. Some physicists have suggested that dark matter might consist of primordial black holes, tiny black holes formed in the chaotic moments after the Big Bang. Others have proposed that dark matter could be composed of exotic forms of matter that exist only under the extreme conditions of the early universe. Still others, particularly those working in theoretical physics, have speculated that dark matter might not be a form of matter at all, but rather an indication that our theories of gravity itself require modification, that perhaps, in the extreme conditions of galaxies and cosmic structures, gravity behaves in ways we do not yet fully understand. The distribution and structure of dark matter. Dark matter, despite its invisibility, shapes the structure of the universe in profound ways. Computer simulations, in which physicists model the universe from the Big Bang to the present day, consistently show that dark matter forms a vast cosmic web, filaments of invisible matter that span billions of light-years, connecting galaxies like pearls on threads of space itself. These filaments concentrate dark matter into halos surrounding galaxies, and galaxies themselves preferentially form within the densest portions of these dark matter structures. The architecture of the universe, then, is determined primarily by this invisible substance. Galaxies, including our own Milky Way, are merely the luminous decorations adorning the dark matter structures that truly define cosmic topology. In a sense, we are witnessing a cosmic inversion of perspective. The visible universe, so magnificent and awe-inspiring to our eyes, constitutes only a minor embellishment within a universe fundamentally structured and dominated by darkness. The implications of this realization extend deeply into our understanding of cosmological history. In the aftermath of the Big Bang, the universe was extraordinarily hot and dense. Matter and radiation were in equilibrium, unable to form structures as we know them. As the universe expanded and cooled, dark matter began to coalesce through gravity, forming the initial gravitational wells into which ordinary matter could later fall. Without dark matter, galaxies would never have formed, stars would never have ignited, and the universe would remain a diffuse soup of particles. In this fundamental sense, dark matter is not merely a curiosity, it is the necessary precondition for our own existence. We are, in a very real sense, prisoners of dark matter's gravity, inhabitants of the universe shaped by its invisible hand. The philosophical implications. The existence of dark matter raises profound philosophical questions about the nature of reality and knowledge. For millennia, humans operated under the assumption that reality consists of what we can perceive. The entire edifice of Western philosophy, from Plato to Descartes to the empiricists of the Enlightenment, grappled with the relationship between perception and reality. Yet here we confront a universe in which the vast majority of matter remains forever inaccessible to direct perception. This revelation suggests something humbling about the nature of human knowledge and the limits of our senses. We are creatures who evolved to perceive the visible spectrum of light, to interact with ordinary matter, to navigate at the scale of the Earth's surface. The universe, however, operates at scales and with constituents that lie far outside the range of our evolved sensory apparatus. Our sciences, our telescopes, our spectrographs, our particle detectors, represent extensions of our senses, tools that allow us to peer beyond the boundaries of our natural perception. Yet even with these tools, the vast majority of the universe's material content remains hidden from us. The mystery of dark matter thus becomes a meditation on the nature of reality itself. What is real? Is reality limited to what we can perceive, or does reality extend into domains forever inaccessible to conscious observation? These are not merely scientific questions but philosophical ones, touching on the very foundations of epistemology, the study of how we know what we know. The physicist and philosopher of science Quentin Milasu might suggest that dark matter represents a form of ancestral reality, a universe that existed long before human consciousness evolved to perceive it, governed by laws indifferent to our ability to observe them. Part 2, Dark Energy and the Acceleration of Cosmic Expansion. The universe's accelerating heartbeat. In 1929, astronomer Edwin Hubble made an observation that revolutionized cosmology. Using the Mount Wilson Observatory in California, one of the most powerful telescopes of its era, Hubble measured the distances and velocities of distant galaxies. He discovered that galaxies are moving away from us, and crucially, that the farther away a galaxy is, the faster it recedes from us. This observation provided the first empirical evidence that the universe itself is expanding, a realization that fundamentally overturned the prevailing assumption of a static, unchanging cosmos. Hubble's discovery led directly to the concept of the Big Bang, the idea that the universe began as an infinitely hot and dense point and has been expanding ever since. This theory, proposed and developed through the work of physicists including Georges Lemaitre, George Gamow, and Fred Hoyle, despite Hoyle's skepticism, he coined the term Big Bang, ironically, became the dominant framework for understanding cosmic history. The universe, according to this model, should be expanding under the influence of gravity, which pulls all matter together and should therefore slow the expansion over time. Imagine throwing a ball upward. Gravity pulls the ball downward, decelerating its upward motion until it reaches a maximum height and falls back to Earth. Physicists hypothesize that the expansion of the universe should behave similarly. Gravity should gradually slow the rate at which galaxies move apart from one another. The question for cosmologists was not whether the expansion would slow, but rather whether it would slow enough that gravity would eventually overcome the initial expansion, causing the universe to eventually collapse back on itself in a big crunch, or whether the expansion would continue indefinitely, with galaxies drifting ever farther apart until the universe became a cold, dark, empty void. To answer this question, astronomers needed to measure the current rate of cosmic expansion and compare it to the rate in the distant past. If the expansion were slowing, then galaxies should have been moving away from us faster in the past than they do today. If galaxies in the distant past were receding faster, then supernovae of a given intrinsic brightness should appear dimmer than expected if they were at the distances implied by their recession velocities. In the 1990s, two independent teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley Laboratory, the other by Brian Schmidt and Adam Rees, embarked on precisely this measurement, using distant type Ia supernovae as cosmic distance markers. The shocking discovery. The results, announced in 1998 and 1999, sent shockwaves through the astronomical community. Rather than finding that the expansion of the universe was slowing, the observations indicated the opposite: the expansion was accelerating. Galaxies were moving apart from one another at an increasing rate. Distant supernovae were dimmer than expected if the universe were merely expanding at a constant rate. The only explanation was that the expansion of the universe was speeding up. This discovery was so unexpected that many astronomers initially suspected an error. Perlmutter, Schmidt, and Rees conducted exhaustive checks and cross-verifications. They examined whether dust might be obscuring the light from distant supernovae, whether the supernovae themselves might behave differently than expected, whether gravitational lensing might distort the observations. Every check confirmed the original finding: the universe's expansion was indeed accelerating. What could cause such an acceleration? The force of gravity attracts all matter toward all other matter. It should slow the expansion, not accelerate it. Some form of anti-gravity force, or more precisely, some form of energy that exerts negative pressure on the fabric of spacetime itself, must be at work. Physicists resurrected an old concept, originally introduced by Albert Einstein in 1917, the cosmological constant, often represented by the Greek letter lambda, lambda. Einstein had introduced the cosmological constant as a modification to his equations of general relativity, proposing a kind of intrinsic repulsive force that permeates the entire universe. Einstein later called the introduction of the cosmological constant the greatest blunder of my life, but perhaps he was premature in his self-criticism. The concept had been vindicated by observation, though in a manner Einstein himself had not anticipated. Dark energy, the universe's expanding mystery. The mysterious force causing the universe's accelerating expansion became known as dark energy. Like dark matter, dark energy is fundamentally mysterious, but whereas dark matter's existence is revealed through its gravitational attraction to ordinary matter, dark energy manifests through its repulsive effect on spacetime itself. Dark energy appears to comprise approximately 68% of the universe's total energy content. Matter, both dark and ordinary, comprises only about 32%. In the cosmic ledger, dark energy is the dominant accounting, the majority constituent of reality itself. The nature of dark energy remains unknown. The simplest hypothesis is that dark energy is indeed Einstein's cosmological constant, a fundamental property of spacetime itself, as inevitable and inexplicable as spacetime's ability to be curved by the presence of mass. According to quantum field theory, even the vacuum of empty space seethes with virtual particles that constantly pop in and out of existence, and this quantum activity contributes an energy density to the universe called vacuum energy or zero-point energy. Perhaps dark energy is this quantum vacuum energy, though calculations attempting to determine the magnitude of this vacuum energy yield results that differ from observations by a factor of 10 to the power of 120, a discrepancy so vast it is often called the worst prediction in the history of physics. Other theoretical physicists have proposed alternative explanations. Some suggest that dark energy might be a scalar field, a field that has a value at every point in space and time, similar to the Higgs field that physicists discovered at the Large Hadron Collider in 2012. This hypothetical field, sometimes called quintessence, could vary from place to place and from time to time, unlike the constant cosmological constant. Other proposals invoke modifications to Einstein's theory of general relativity itself, suggesting that perhaps gravity behaves differently on cosmological scales than our current theories predict. The ultimate fate, the Big Freeze. The discovery of dark energy and the acceleration of cosmic expansion has profound implications for the ultimate fate of the universe. In the past, cosmologists debated whether the universe would expand forever or eventually collapse. The accelerating expansion provides a sobering answer: the universe will expand forever, and the process will accelerate. In the distant future, trillions of years hence, the universe will become increasingly cold and empty. Galaxies will continue to recede from one another, their light rendered redder and fainter by the expanding space between them. Eventually, galaxies beyond our local cluster of galaxies will recede so far that their light can never reach us, even traveling at the speed of light. The universe will become a scattered collection of isolated galaxies, each surrounded by a dark void that stretches forever. Within these surviving galaxies, stars will gradually exhaust their fuel and cease to shine. Stellar remnants, white dwarfs, neutron stars, and black holes, will remain, slowly cooling. Over timescales so vast they challenge human comprehension, even these remnants will decay. Protons, the building blocks of atoms, may not be eternally stable. If proton decay occurs, then all ordinary matter will gradually disintegrate, leaving only photons, neutrinos, and other elementary particles scattered throughout an ever-expanding void. This ultimate fate of the universe, often called the heat death or Big Freeze scenario, arises directly from our discovery of dark energy and the acceleration it imparts to cosmic expansion. It is a sobering vision, a universe destined to become infinitely cold, infinitely sparse, and infinitely lonely. Yet this vision also carries a strange beauty. For billions of years into the future, for as long as stars continue to shine and conscious beings continue to emerge in the universe, there will be warmth, light, complexity, and perhaps meaning. The current era of cosmic history, in which galaxies are filled with stars and consciousness has emerged to contemplate the cosmos, represents a fleeting epoch of brightness within an universe ultimately destined for eternal darkness. Philosophical contemplation, the indifference of the cosmos. The existence of dark energy confronts us with a deeply unsettling realization: the universe appears to be fundamentally indifferent to our existence. The force causing cosmic expansion to accelerate is not balanced by any counterforce that maintains stability or promotes the emergence of life. Rather, dark energy seems to drive the universe inexorably toward a state of maximum entropy, maximum isolation, and maximum emptiness. This realization echoes the philosophical positions articulated by thinkers such as Arthur Schopenhauer and later the existentialists. The universe is not designed for our benefit, nor arranged to make human existence meaningful. The cosmos operates according to physical laws indifferent to consciousness, and these laws appear to be driving the universe toward a state hostile to all life and complexity. And yet, here we stand, conscious beings capable of understanding these cosmological principles. Our very capacity to comprehend the universe's ultimate fate, to measure the acceleration of cosmic expansion, to theorize about dark energy, this represents something remarkable. The universe has given rise to structures complex enough to contemplate the universe itself. In the finite existence of conscious observers, in the brief window of cosmic history when stars shine and complexity emerges, there is a profound poignancy. We are the universe becoming aware of itself, however temporarily, however briefly in the grand span of cosmic time. Part 3, The Singularity and the Beginning of Everything. Before the beginning, the conceptual abyss. What came before the Big Bang? This deceptively simple question leads us to the very edge of human cognition, where physics and philosophy merge into something that defies easy categorization. The physicist Stephen Hawking argued that the question is meaningless in a particularly subtle way. In his no-boundary proposal, Hawking suggested that spacetime is finite but unbounded. Imagine, he proposed, the surface of a sphere. You can travel forever on the surface of a sphere, yet the surface is finite and has no boundary. Similarly, Hawking argued, the universe may be finite in its temporal extent but have no beginning in the sense of a moment zero. More conventionally, the Big Bang theory posits that our universe emerged from an infinitely hot and infinitely dense point, a singularity, approximately 13.8 billion years ago. But what does it mean for something to emerge from nothing? What preceded this moment of cosmic creation? The honest answer, from contemporary physics, is that we do not know. Our current theories break down at the moment of the Big Bang itself. General relativity, which beautifully describes gravity and the large-scale structure of spacetime, predicts that the universe's expansion should reverse if we trace time backward, leading to a moment of infinite density and temperature where the theory itself becomes meaningless. The physicist and cosmologist Alan Guth has described this situation poetically: the universe may be the ultimate free lunch. The net energy of the universe might be zero, the positive energy of matter and radiation balanced by the negative energy of gravity. In this view, creating a universe from nothing requires no energy, no external power source. The universe could spontaneously emerge from quantum fluctuations in an underlying vacuum, much like virtual particles constantly pop into and out of existence at subatomic scales. The Big Bang and the first moments. Let us imagine ourselves witnesses to the birth of the universe, traveling backward through time from the present moment to the moment of cosmic creation. We move backward through billions of years of cosmic expansion, galaxies moving closer together, space becoming hotter and denser. We travel back through the formation of galaxies, back through the recombination era when the universe transitioned from a plasma of particles to neutral atoms and light could travel freely. We move back through the nuclear synthesis era, when the first atomic nuclei were forged in the intense heat of the early universe. We travel back further still, to microseconds after the Big Bang. At 1 microsecond after the Big Bang, the universe's temperature was measured in trillions of Kelvin. At this moment, the strong nuclear force, which binds quarks together into protons and neutrons, was becoming distinct from the other fundamental forces. Particles called pions, consisting of quarks and antiquarks, were being produced and annihilated constantly in the roiling quantum chaos. At 1/1,000,000th of a second after the Big Bang, the temperature had dropped to 1,000,000,000,000 Kelvin, and the universe was transitioning from a state of quark-gluon plasma, quarks and gluons mingling freely, to a state where quarks were becoming confined into hadrons. This transition, called the hadron-quark transition or quark-gluon deconfinement, represents a profound restructuring of matter itself. At 1 second after the Big Bang, the temperature had fallen to 10 billion Kelvin, and an extraordinary process called neutrino decoupling occurred. Neutrinos, ghostly particles that barely interact with ordinary matter, ceased to interact with the other constituents of the early universe and began an independent existence. Even today, our universe is filled with these primordial neutrinos, created in the Big Bang, a cosmic reminder of those first turbulent moments. The era of cosmic inflation, a revolutionary concept. In the early 1980s, physicist Alan Guth introduced a revolutionary concept to cosmology: cosmic inflation. According to the inflationary hypothesis, in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, doubling in size perhaps 20 times in the span of a trillionth of a second. This would seem like an extreme extrapolation, yet inflation solves numerous problems that plagued the standard Big Bang theory. One such problem was the horizon problem. When we observe the cosmic microwave background radiation, the afterglow of the Big Bang, we find it to be remarkably uniform. The radiation reaching us from opposite sides of the universe is at the same temperature to an accuracy of 1 part in 100,000. Yet according to the standard Big Bang theory, opposite sides of the observable universe should never have been in contact with one another. They should be causally disconnected regions that never had the opportunity to equilibrate to the same temperature. How, then, could the entire universe have the same temperature? Inflation provides an elegant solution. If all the space we can observe today was originally compressed into a tiny region much smaller than a subatomic particle, then this region could easily have been in thermal contact before inflation expanded it to cosmic scales. Inflation stretched this originally uniform region to enormous dimensions, carrying its uniformity across what is now the entire observable universe. Another problem that inflation solves is the flatness problem. Observations indicate that the universe's geometry is remarkably flat, that is, the curvature of spacetime is extraordinarily close to zero. This flatness is unusual and requires a very specific set of initial conditions. Inflation naturally produces a flat universe, just as inflating a balloon makes the surface increasingly flat, though of course the balloon itself is curved in 3 dimensions. The cosmic microwave background, the universe's fingerprints. One of the most profound pieces of evidence for the Big Bang theory, and particularly for the inflationary hypothesis, comes from observations of the cosmic microwave background radiation, CMB. This radiation represents the earliest light we can observe, photons released when the universe transitioned from a plasma state to a neutral state, approximately 380,000 years after the Big Bang. In 1964, Arno Penzias and Robert Wilson, working at Bell Telephone Laboratories, discovered this radiation accidentally while attempting to eliminate noise from a sensitive radio antenna. They had assumed the uniform noise they detected was simply equipment malfunction, but colleagues recognized it as the predicted afterglow of the Big Bang. This discovery earned Penzias and Wilson the Nobel Prize and provided powerful confirmation of the Big Bang theory. More recently, sophisticated satellite observations by COBE, Cosmic Background Explorer, WMAP, Wilkinson Microwave Anisotropy Probe, and Planck have mapped the cosmic microwave background with extraordinary precision. These maps reveal tiny temperature fluctuations, deviations of 1 part in 100,000 from the average temperature. These minute variations are of profound importance. They represent the seeds from which galaxies, galaxy clusters, and all the structure we observe in the universe grew through gravitational amplification. According to inflationary theory, these temperature fluctuations originated as quantum fluctuations at the subatomic scale, stretched to cosmic dimensions by inflation. The largest structures we observe in the universe, superclusters of galaxies spanning 1 billion light-years, emerged from quantum fluctuations smaller than an atom. This represents perhaps the most stunning marriage of the extremely small and the extremely large in all of physics. The quantum realm of subatomic particles generated the structures and variations that shape the cosmos itself. The nature of the singularity, where physics fails. As we trace cosmic history backward toward the moment of the Big Bang, we encounter a profound conceptual barrier. The equations of general relativity predict that density and temperature increase without bound as we approach the Big Bang singularity. Physical quantities, density, temperature, curvature of spacetime, become infinite. In the language of mathematics, the equations become singular, their solutions undefined. This singularity represents not merely an extreme condition but a fundamental failure of our theoretical framework. General relativity, extraordinarily successful at describing gravity across all scales from planetary orbits to cosmological structures, breaks down at the singularity. The physics of the singularity lies beyond the reach of our current theories. To describe the singularity, we would need a theory of quantum gravity, a theory that unified quantum mechanics and general relativity. String theory, loop quantum gravity, and other approaches attempt to construct such a unified theory, but none has achieved empirical confirmation. In string theory, for instance, the universe might have additional dimensions beyond the four we experience, 3 of space and 1 of time, curled up at scales too small to observe directly. The Big Bang singularity, in this framework, might represent a transition between different topological configurations of these extra dimensions. Loop quantum gravity takes a different approach, suggesting that spacetime itself is quantized at the Planck scale, approximately 10 to the power of -35 meters. At these scales, spacetime is not smooth but granular, composed of discrete quanta of geometry. In this picture, the Big Bang singularity might be replaced by a quantum bounce, a maximum density after which the universe would have contracted and then re-expanded in a cyclic process. These are speculations, educated guesses by brilliant physicists working at the absolute frontier of human knowledge. Yet they remain unverified. The nature of the Big Bang singularity, the origin of the universe itself, remains one of the deepest mysteries in physics. The philosophical question of creation. The Big Bang theory, combined with inflationary cosmology, presents us with a cosmos that appears to have had a definite beginning. This raises profound philosophical questions about existence, causation, and creation. Medieval theologians debated whether a universe with a beginning was more compatible with the idea of God than an eternal universe. Some argued that creation ex nihilo, creation from nothing, was necessary to demonstrate God's omnipotence. Others suggested that an eternal universe better reflected divine nature. The physicist and philosopher of science Paul Davies has written extensively about the apparent fine-tuning of the universe. Numerous physical constants and initial conditions appear to be precisely calibrated to allow for the emergence of complexity and life. If these constants were slightly different, the universe would either have expanded so rapidly that galaxies never formed, or collapsed back on itself too quickly for stars and life to emerge. The gravitational constant, the strength of the strong and weak nuclear forces, the mass of the electron, these and numerous other parameters appear calibrated to a remarkable degree. Some physicists and philosophers have interpreted this fine-tuning as evidence for design, suggesting that a divine creator fine-tuned the universe to permit life. Others invoke the anthropic principle, pointing out that we necessarily observe a universe compatible with our existence. It would be unsurprising that our universe appears fine-tuned because we could not observe a universe in which we did not exist. Still others propose the many worlds hypothesis, suggesting that our universe is merely one among an infinite multitude of universes with different physical laws and constants. In this framework, we inhabit one of the rare universes whose parameters happen to permit life and observers. The mystery of cosmic origin thus extends beyond physics into metaphysics and philosophy. We may never definitively answer the question of why there is something rather than nothing, or whether the universe's beginning requires an external explanation or whether it is ultimate and inexplicable. Yet the pursuit of these questions, the attempt to understand our cosmic origins and our place within the universe, represents one of humanity's most profound endeavors. Part 4. The Search for Intelligent Life Beyond Earth. The Drake Equation, Quantifying the Odds. In 1961, astronomer Frank Drake assembled a group of scientists at the National Radio Astronomy Observatory in Green Bank, West Virginia, to discuss the possibility of detecting extraterrestrial civilizations. In preparation for this meeting, Drake formulated what has become known as the Drake Equation, a framework for estimating the number of communicative civilizations in our galaxy. The Drake Equation attempts to express the number of communicative civilizations, n, as the product of several factors, n equals r asterisk times fp times ne times fl times phi times fc times l, where each term represents a probability or rate. R** is the rate at which stars form in the galaxy, Fp is the fraction of stars that have planets, Ne is the average number of planets per star capable of supporting life, Fl is the fraction of suitable planets on which life emerges, Phi is the fraction of life-bearing planets on which intelligent life develops, Fc is the fraction of intelligent civilizations that develop technology capable of communication, and L is the average lifetime of such technological civilizations. Each of these terms presents a formidable challenge to estimate. Estimates for some parameters have become more precise with advances in astronomy. We now know, thanks to decades of exoplanet research, that planets are extraordinarily common. Nearly every star hosts at least one planet, and perhaps the majority host multiple planets. The parameter Fp, once thought to be small, is now estimated to be close to 1. Other parameters remain deeply uncertain. The likelihood that a planet with liquid water will develop life, the parameters Fl and Phi, remains unknown. No planet beyond Earth provides us data on this probability. Some scientists, influenced by the principle of mediocrity, the idea that we should not assume Earth to be special or exceptional, suggest these probabilities might be relatively high. Others, noting how contingent and improbable the emergence of life seems, suggest these probabilities might be extraordinarily low. The parameter L, the average lifetime of technological civilizations, may prove decisive. If technological civilizations typically destroy themselves through nuclear war, environmental degradation, or other catastrophes within a few centuries of developing technology, then L would be small, and the number of communicative civilizations would be correspondingly small or zero. If civilizations learn to navigate their existential crises and survive for millions or billions of years, then L would be large, and the galaxy might teem with civilization. The Fermi paradox, the silence of the stars. In the same era that Drake formulated his equation, physicist Enrico Fermi, conversing with colleagues about the possibility of extraterrestrial life, reportedly asked a pointed question: where is everybody? This simple question encapsulates what has become known as the Fermi paradox, the apparent contradiction between the high probability that extraterrestrial civilizations should exist, suggested by the Drake equation, and the vastness of the universe, and our complete lack of evidence for their existence. The observable universe contains approximately 2 trillion galaxies, each containing hundreds of billions of stars. If intelligent life is common, we might expect to observe evidence of extraterrestrial civilizations, radio signals, optical beacons, megastructures constructed by advanced civilizations, or visits from spacecraft. Yet we observe nothing. The universe, insofar as we have searched it, appears silent. No signals have been detected despite decades of searching through the SETI, Search for Extraterrestrial Intelligence, program. No technological artifacts have been discovered. No visits from spacecraft have been documented. This paradox admits numerous possible explanations, each unsettling in its own way. Perhaps the simplest explanation is that intelligent life is extraordinarily rare, so rare that the nearest technological civilization is thousands of light-years distant, beyond the practical reach of communication with current technology. If civilizations are separated by such vast distances, communication would be extraordinarily difficult, especially given the enormous time delays in electromagnetic signals. A more pessimistic explanation involves what is sometimes called the Great Filter, an aspect of cosmic evolution that severely limits the emergence of advanced technological civilizations. Perhaps the Great Filter lies in our past, suggesting that the emergence of life, or of intelligent life, is so extraordinarily improbable that we are the only observers in our galactic neighborhood. Or perhaps the Great Filter lies in our future, suggesting that technological civilizations inevitably destroy themselves before developing the capacity for interstellar communication or travel. This latter possibility carries darker implications. It suggests that our own future may follow a similar path. Alternative explanations and the zoo hypothesis. Some scientists and philosophers have proposed more exotic explanations for the Fermi paradox. The zoo hypothesis, popularized by John Ball, suggests that extraterrestrial civilizations may exist but have chosen not to contact us, either out of respect for our development as a species, or for purposes of scientific study. In this hypothesis, we are like animals in a zoo, observed but not contacted by more advanced civilizations who maintain a policy of non-interference. The concept of the zoo hypothesis raises intriguing questions about the ethics of contact and the potential consequences of revealing the existence of extraterrestrial life to a developing civilization. Would such contact accelerate our scientific and technological progress, or would it cause societal disruption and conflict? Would older, more advanced civilizations have an ethical obligation to shield younger civilizations from knowledge of their existence, or would such concealment violate principles of free knowledge and autonomy? Other scientists have proposed that the Fermi paradox might be explained by temporal factors. If civilizations are created throughout cosmic history, then at any given moment, only a tiny fraction of potential civilizations would be at technological maturity. The age of the Earth is approximately 4.5 billion years, the universe is nearly 3 times as old. Perhaps intelligent civilizations arose earlier in cosmic history, flourished, and then perished, before any overlapped with our era. Still others have suggested that communication might be more difficult than we imagine. Perhaps extraterrestrial civilizations use forms of communication so different from radio and optical signals that we would not recognize them. Perhaps they communicate using quantum entanglement or wormholes or other exotic methods predicted by theoretical physics. Perhaps their signals are so faint or so cleverly hidden that our current instruments cannot detect them. SETI and the search for signals. The search for extraterrestrial intelligence represents humanity's most systematic attempt to answer the question posed by Fermi. Beginning in 1960 with Frank Drake's Project Ozma at the National Radio Astronomy Observatory, SETI programs have scanned the skies for artificial signals that would indicate the presence of technological civilizations. SETI searches have used increasingly sensitive equipment, examining ever larger portions of the electromagnetic spectrum. Advances in computing have allowed signals to be processed and analyzed with greater sophistication. The Breakthrough Listen initiative, funded by physicist Yuri Milner, represents the most comprehensive SETI search to date, examining billions of frequencies from thousands of nearby stars. Despite the sophistication of these searches, no confirmed extraterrestrial signal has been detected. There have been intriguing candidates, most famously the WOW signal, detected in 1977, a narrowband radio signal of apparent extraterrestrial origin that has never been explained or repeated. Yet none has risen above the level of ambiguity to provide definitive evidence of extraterrestrial intelligence. The search itself, regardless of outcome, represents something profound about human nature. We extend our ears toward the cosmos, hoping to hear voices other than our own. We broadcast messages into space, hoping that somewhere, someone listens. The act of searching for extraterrestrial intelligence is simultaneously an act of hope and an acknowledgement of loneliness, a hope that we are not alone, coupled with a growing awareness that silence might be the answer we receive. Panspermia and the distribution of life. While SETI searches the cosmos for intelligent signals, other scientists have explored the possibility that life itself might travel between worlds through what is called panspermia, the process by which organisms or organic compounds are transferred between planets or even between star systems. Evidence suggests that meteorites regularly transfer material between planets. Meteorites from Mars, ejected by asteroid impacts, have reached Earth. It is conceivable that such meteorites could carry microbial life, which, if protected within rock or dormant in spore form, might survive the journey through space and the trauma of impact on another world. Laboratory experiments have shown that some terrestrial microorganisms can survive conditions similar to the vacuum of space and the radiation environment of interplanetary travel. If panspermia occurs, it could profoundly alter our understanding of life's distribution throughout the cosmos. Life might have originated on one world and spread to numerous others. Alternatively, panspermia might represent a minor factor in the broader picture of life's emergence. Even if panspermia is possible, it does not solve the fundamental mystery of how life originated in the first place. The question of life's origin, abiogenesis, the emergence of life from non-living chemical systems, remains one of the deepest unsolved problems in science. We do not yet understand the chemical processes by which the chemical ingredients of early Earth, water, carbon dioxide, nitrogen, and various minerals, spontaneously organize themselves into self-replicating molecules capable of evolution. We have laboratory demonstrations of how certain organic molecules can form under conditions hypothesized for the early Earth, and we have shown that RNA molecules can self-replicate under certain conditions. Yet the path from non-living chemistry to living cells remains obscure. Part 5: The Puzzle of Consciousness and the Mind. The hard problem: subjective experience in an objective universe. Few mysteries in science are as profound or as personally relevant as the mystery of consciousness. We exist. We experience the world. We see colors, hear sounds, feel emotions, contemplate ideas. Yet none of this seems explicable purely in terms of physical processes. When neuroscientists examine the brain, they find neurons firing, neurotransmitters binding to receptors, electromagnetic fields fluctuating. Yet nowhere in this physical description do we find an explanation for why any of this should feel like something, why there should be subjective experience, what philosophers call qualia. The philosopher David Chalmers has termed this, the hard problem of consciousness, distinguishing it from the easy problems, which are merely very difficult, not in principle intractable, of explaining how the brain processes information, controls behavior, and integrates sensory data. The hard problem is, why should any of these physical processes be accompanied by subjective experience? Why should there be something it is like to see red, or to taste coffee, or to feel pain? Consider a thought experiment. Imagine a neuroscientist who has studied color perception so thoroughly that she understands perfectly every physical process involved in the perception of red color. She understands which neurons fire, which neurotransmitters are released, which areas of the cortex light up. Yet she herself has never seen red, she is colorblind to that particular wavelength. When she finally becomes able to see red through some hypothetical medical intervention, does she learn something new? Does she gain knowledge that was not deducible from all her previous physical knowledge of color perception? Most people's intuition suggests that she does indeed learn something new, what philosophers call knowing what it's like to see red. This intuition has suggested to many philosophers and scientists that consciousness is not fully explicable in purely physical terms. There seems to be a residual explanatory gap, a gulf between objective physical description and subjective experience. The neural correlates of consciousness. While the hard problem remains unsolved, neuroscience has made remarkable progress in identifying the neural correlates of consciousness, the brain structures and neural processes associated with conscious experience. Functional magnetic resonance imaging, fMRI, allows researchers to observe which parts of the brain are active while subjects perform various tasks or report conscious experiences. These studies have revealed that consciousness appears to depend on communication between widespread networks of neurons. The default mode network, a collection of brain regions that are active during rest and mind wandering, appears important for self-referential thinking and conscious experience. The salience network, involving the anterior insula and anterior cingulate cortex, appears to filter sensory information and direct attention to the most important stimuli. The central executive network, involving the prefrontal cortex, appears involved in planning, decision-making, and complex reasoning. Remarkably, different levels and types of consciousness appear to correlate with different patterns of neural activity. During deep sleep without dreams, regions involved in self-awareness and time perception show reduced activity, and subjects report no consciousness upon waking. During REM sleep, when vivid dreams occur, there is significant activity in visual and emotional processing regions, and subjects report conscious experiences of dreams, albeit often strange and illogical. Brain injuries and neurological diseases have provided invaluable insights into consciousness. Patients with split brain syndrome, in whom the corpus callosum connecting the two cerebral hemispheres has been severed surgically, exhibit fascinating dissociations of consciousness. The two hemispheres can be presented with different information and respond independently, suggesting that consciousness might not be singular and unified but rather a construction or an illusion of unified awareness created by the brain's interpretation of its diverse components. Patients in vegetative states, conscious states in which patients waken but show no signs of awareness, have sometimes been shown through advanced brain imaging to have retained some form of consciousness. Some such patients, when asked to imagine playing tennis or visiting their home, show patterns of fMRI activation in motor and navigation areas similar to non-impaired individuals. This has opened the possibility that some patients without behavioral signs of consciousness may nevertheless retain inner experience. The quantum mind hypothesis. Some physicists and philosophers have proposed that consciousness might involve quantum mechanical processes not yet understood by science. The physicist Roger Penrose and anesthesiologist Stuart Hameroff have argued that microtubules, structures within neurons, might utilize quantum effects such as superposition and quantum tunneling to produce consciousness. In this view, consciousness would emerge from quantum processes that amplified to macroscopic scales through a process called objective reduction. This hypothesis remains speculative and lacks substantial empirical support. Most neuroscientists are skeptical that quantum effects play a crucial role in consciousness, given that the brain operates at temperatures and energy scales where quantum effects are typically suppressed by decoherence, the interaction of quantum systems with their environment. Yet the hypothesis raises intriguing questions about the limits of our understanding. Perhaps consciousness does involve physical processes that we have not yet identified, and perhaps such processes might operate in unexpected ways at the interface between quantum and classical mechanics. The physicist John von Neumann noted in the early days of quantum mechanics that the theory seemed to require a conscious observer to collapse the wave function and determine physical reality. Some interpretations of quantum mechanics, such as the von Neumann-Wigner interpretation, have proposed that consciousness plays a fundamental role in quantum mechanics. These ideas remain highly speculative and have not achieved consensus among physicists, but they suggest that consciousness might be more fundamental to the nature of reality than the standard materialist framework suggests. The problem of other minds. Even if we solved the hard problem of consciousness for our own subjective experience, an equally puzzling question remains: how do we know that other beings are conscious? You can observe directly the conscious experiences of your own mind, but you cannot directly access anyone else's subjective experience. Other people might be mere philosophical zombies, beings that behave as if conscious, responding intelligently to stimuli and reporting conscious experiences, yet lacking any inner experience whatsoever. This problem of other minds admits no logical solution. We cannot prove that other humans are conscious, we can only infer it by analogy. We observe that other humans have brains similar to our own, behave in ways that suggest consciousness, and report subjective experiences similar to our own. We assume they are conscious because they are like us. But this assumption, while reasonable, cannot be logically proven. The problem becomes more acute as we expand our circle of moral concern. We may reasonably assume that other humans are conscious because they are neurologically and behaviorally similar to us. But are non-human primates conscious? The evidence suggests yes, given their complex behavior and neurological similarities to humans. But what about other mammals? What about birds, fish, and insects? Some birds and mammals display remarkable cognitive abilities, problem solving, tool use, play, that suggest consciousness. Yet the farther we move from humans, the less certain we can be. This uncertainty has profound ethical implications. If we cannot know whether other beings are conscious, on what grounds do we justify harming them or failing to consider their interests? The precautionary principle might suggest that in cases of uncertainty about consciousness, we should err on the side of caution and assume consciousness is present in beings that display complex behavior and brain structures that might support consciousness. Panpsychism, consciousness as fundamental. Frustrated by the explanatory gap between physical processes and consciousness, some philosophers have proposed a radical alternative, panpsychism, the view that consciousness is a fundamental feature of the universe, present in varying degrees in all matter. In this view, electrons, atoms, and simple organisms might possess elementary forms of consciousness. Complex consciousness, as experienced by humans, would then emerge through the combination and integration of these more elementary conscious properties. Panpsychism resolves the hard problem by stipulating that consciousness is not something that needs to emerge from purely physical processes, rather, consciousness is an intrinsic aspect of physical properties themselves. Just as mass and charge are fundamental properties of particles, perhaps consciousness is as well. Critics argue that panpsychism merely relocates the mystery without solving it. Even if we grant that consciousness is a fundamental property, we have not explained why it should exist or how its presence in simple particles gives rise to human consciousness. Additionally, panpsychism seems to contradict our intuitions about consciousness. It seems implausible that an electron or atom should possess any form of consciousness. Yet panpsychism has found increasing support among contemporary philosophers of mind, including David Chalmers, Galen Strawson, and others. It represents an acknowledgement of how profoundly difficult the consciousness problem truly is. When all attempts to explain consciousness in terms of known physical processes fail, and the explanatory gap seems unbridgeable, perhaps consciousness must be treated as a fundamental feature of reality rather than an emergent property. The future of consciousness studies. As neuroscience advances and our understanding of brain processes deepens, consciousness remains elusive. Perhaps consciousness will be explained as advances in neuroscience reveal previously unknown aspects of brain function. Perhaps consciousness will be shown to be an illusion, a useful fiction that the brain constructs. Perhaps consciousness will be understood as a fundamental feature of reality, present throughout the universe in varying degrees. Or perhaps consciousness will remain an irreducible mystery, forever challenging our attempts at scientific explanation. The mystery of consciousness connects directly to questions about life and intelligence in the universe. If consciousness is rare or unique to humans, we may be special in a way that resolves the Fermi paradox. Perhaps intelligent life capable of technology and civilization is extraordinarily rare. If consciousness is common, spread throughout the universe in the minds of countless beings, then we are not special in this regard, yet the silence of the cosmos becomes more puzzling. Perhaps consciousness itself, or the ability to develop complex civilization, requires conditions rarer than we realize. Part 6, Black Holes, where reality breaks down. Stellar collapse and the discovery of black holes. In 1783, 2 centuries before Einstein's general relativity, the English clergyman and physicist John Michell made a remarkable prediction. Reasoning from Newton's laws of gravity and the concept of escape velocity, Michell calculated that a star sufficiently massive and sufficiently compact could generate a gravitational field so strong that light itself could not escape. Nothing could be faster than light, so nothing could escape such an object. Michell called such objects dark stars. Michell's prediction was mathematically sound but remained purely theoretical. At the time, no observations suggested such objects existed. The concept faded into obscurity for nearly 2 centuries until Einstein's theory of general relativity was formulated. According to general relativity, massive objects warp the fabric of spacetime itself. Massive stars, near the end of their lives, can collapse under their own gravity if they are sufficiently massive. The German physicist Karl Schwarzschild, solving Einstein's equations for a spherically symmetric mass distribution, found that an object sufficiently massive and compact would possess a region from which no light could escape, precisely Michel's dark star, now understood through the framework of general relativity. The boundary of this region, called the event horizon, represents a point of no return. An object crossing the event horizon can never return to the outside universe. Even light, traveling at the universal speed limit, cannot escape. The region inside the event horizon is forever causally disconnected from the rest of the universe, a sealed chamber from which no information can escape. In 1967, physicist John Wheeler coined the term black hole to describe these exotic objects. The term perfectly captures the nature of these objects, regions of spacetime so twisted by gravity that they appear as holes in the universe, regions from which neither matter nor light can escape. The universe, apparently, contained these extreme objects formed by the collapse of massive stars. The physics of black holes. A black hole of stellar mass, perhaps 10 to 20 times the mass of the Sun, compressed into a region only a few kilometers across, represents the ultimate extreme of gravitational effects. Near a black hole, spacetime curvature becomes extreme, and relativistic effects dominate. Time itself is distorted near the event horizon. An observer far from a black hole, watching another observer fall toward the event horizon, would see the falling observer's clock slow down as the event horizon approached. The falling observer would see themselves approach the event horizon in finite time, but from the distant observer's perspective, the process would appear to slow asymptotically, never quite reaching the event horizon. This extreme distortion of time and space suggests that black holes represent a kind of limit or boundary in physics. Experiments using GPS satellites have demonstrated relativistic time dilation to great precision. Clocks on satellites, moving faster and in weaker gravity than clocks on Earth, tick slightly faster. Yet these effects are minute compared to the extreme effects near a black hole's event horizon. Black holes were once thought to be completely black, regions from which nothing could escape, not even information. If matter fell into a black hole, that information would be forever lost to the universe. This would violate a fundamental principle of physics called unitarity, which states that information is never destroyed, merely transformed or redistributed. Hawking radiation, black holes are not forever. In 1974, Stephen Hawking made a startling discovery that revolutionized our understanding of black holes. Using quantum field theory applied near the event horizon of a black hole, Hawking showed that black holes are not entirely black. Due to quantum fluctuations near the event horizon, particle-antiparticle pairs can spontaneously form just outside the event horizon. If one member of the pair falls into the black hole while the other escapes, the escaping particle would appear to an external observer as radiation emitted by the black hole. The black hole would gradually lose mass as it radiates, eventually evaporating completely in a violent explosion. This Hawking radiation, as it came to be known, was entirely unexpected. It suggested that black holes, those supreme examples of gravity's power, could be slowly consumed by quantum mechanical processes, a remarkable interplay between general relativity's domain of gravity and quantum mechanics' domain of subatomic physics. The implications were profound. It meant that black holes could not be truly eternal sinks of matter and energy. They would eventually evaporate. However, the process would be extraordinarily slow for stellar mass black holes. A black hole of 10 solar masses would take approximately 2 times 10 to the power of 67 years to completely evaporate through Hawking radiation, far, far longer than the current age of the universe. The information paradox. Yet Hawking radiation presented a paradox. If a black hole evaporates, what happens to the information about all the matter and energy that fell into it? According to general relativity, once matter crosses the event horizon, all information about it is lost to the external universe. But according to quantum mechanics, information cannot be destroyed. The process must be reversible in principle, meaning that given complete knowledge of the initial state and the evolution laws, one could in principle reconstruct the history of the system. How could both be true? This contradiction, known as the black hole information paradox, has occupied the attention of theoretical physicists for decades. Some physicists, including Stephen Hawking himself in his later work, propose that black holes actually do preserve information in subtle correlations within the radiation they emit, that is, despite appearances, the radiation is not completely random but contains encoded information about the black hole's prior history. Others have proposed that the apparent loss of information represents a genuine violation of quantum mechanics, requiring a modification to quantum field theory. Still others suggest that the paradox will only be resolved through a complete theory of quantum gravity that unifies quantum mechanics and general relativity. The black hole information paradox thus represents a deep conflict between two of physics' most successful and best-tested theories. Resolution of this conflict will likely require revolutionary insights into the fundamental nature of spacetime, information, and reality itself. Supermassive black holes and galactic cores. While stellar mass black holes formed from the collapse of massive stars represent remarkable objects, observations in recent decades have revealed something even more astonishing. Most galaxies, including our own Milky Way, contain supermassive black holes at their cores, objects millions or billions of times more massive than the Sun. The supermassive black hole at the center of the Milky Way, called Sagittarius A*, has a mass of approximately 4 million solar masses, compressed into a region the size of our solar system. Yet despite its enormous mass, the gravitational effects of Sagittarius A* on Earth are negligible. The universe is so vast that even a supermassive black hole at the center of our galaxy has essentially no effect on our planetary orbits. The origin of supermassive black holes remains mysterious. Stars collapse to form stellar mass black holes, but the process by which supermassive black holes form is not fully understood. Perhaps they grow through the merger of smaller black holes over billions of years of galactic history. Perhaps they form directly from the collapse of massive gas clouds in the early universe. Or perhaps the mechanism is some combination of these processes. The exact formation scenario remains an area of active research in astrophysics. Supermassive black holes appear to play a crucial role in galactic evolution. Gas spiraling into a supermassive black hole releases tremendous energy, powering violent outflows that can affect the entire galaxy. These black hole-driven processes may regulate the formation of stars and the growth of galaxies, suggesting that black holes, rather than being merely exotic objects on the periphery of galactic structure, may be central to understanding how galaxies form and evolve. The Event Horizon Telescope, seeing the invisible. For decades, black holes were theoretical predictions confirmed only through indirect observations. Astronomers detected X-rays from material spiraling into black holes, measured the orbits of stars around a supermassive black hole at the galactic center, and observed jets of material ejected by black holes. Yet no direct image of a black hole itself had ever been obtained. In 2019, this changed. The Event Horizon Telescope, a global array of radio telescopes combined to create an instrument with an effective diameter equal to Earth's diameter, produced the first direct image of a black hole. The target was the supermassive black hole at the center of the galaxy M87, a giant elliptical galaxy approximately 55 million light-years distant. The image showed a bright ring of material surrounding a dark central region, the shadow of the black hole, where light is trapped by the immense gravitational field. The image was both a triumph of observational astronomy and a moment of profound philosophical significance. We were seeing, directly, a region of spacetime so extreme that it defied intuition. We were seeing the shadow of infinity, the silhouette of a region where gravity was so strong that reality itself seemed to break down. Part 7, Time, Causality, and the Flow of Time. The arrow of time, why does time flow forward? Among the deepest mysteries in physics lies a question so fundamental that we often fail to notice its profundity: why does time flow only in one direction? We experience time as moving forward from past to future. We remember the past but not the future. Events can cause other events, but effects never precede causes. Yet the fundamental equations of physics, those of classical mechanics, general relativity, and quantum mechanics, are symmetrical in time. They work equally well if you reverse the direction of time. Consider Newton's second law, F equals ma. This equation describes how forces cause accelerations. If you reverse time, replacing t with t, the equation remains valid. A planet in orbit follows the same equations regardless of whether we run the clock forward or backward. There is nothing in the fundamental laws that requires time to flow forward rather than backward. Yet clearly, time does flow forward. We are born, we age, we die, never the reverse. A cup falls from a table and shatters. We never observe broken shards of pottery spontaneously assembling themselves and jumping back onto the table. The entropy of an isolated system always increases. This is the second law of thermodynamics. This forward directionality of time is called the arrow of time. The resolution of this paradox lies in entropy, the measure of disorder or the number of available states a system can occupy. The second law of thermodynamics states that the entropy of an isolated system increases over time. A clean, organized cup has low entropy. The scattered shards and dust of a shattered cup have high entropy. As time progresses, physical systems evolve towards states of higher entropy. But entropy is fundamentally statistical. A system of gas molecules in a box will tend toward a uniform distribution throughout the box rather than clustering in one corner. This is not because there is some force pushing molecules toward uniformity, but because there are far more states corresponding to a uniform distribution than to a clustered distribution. A uniform distribution is more probable, simply because there are more ways for molecules to be arranged uniformly. The arrow of time emerges from the initial conditions of the universe. The Big Bang created the universe in a state of extraordinarily low entropy, an ordered, hot, dense universe. Since that time, the universe has been evolving toward higher entropy, becoming increasingly disordered and cold. The arrow of time we experience is the result of this cosmic evolution from low entropy in the past to high entropy in the future. The block universe, the illusion of flow. Einstein's theory of special relativity introduced a revolutionary conception of time. In classical mechanics, time is absolute, it flows at the same rate for all observers everywhere. In special relativity, time is relative, it flows at different rates for observers in different reference frames. More profoundly, special relativity suggests that the distinction between past, present, and future may be illusory. In relativity, spacetime is a unified four-dimensional continuum. Space and time are not separate, they are dimensions of a single structure. Some physicists and philosophers have argued that this suggests a block universe interpretation, past, present, and future all exist equally. The flow of time that we experience is merely the result of our consciousness traversing the block universe along a particular path. In this view, your birth, your current moment, and your death all exist equally in the block universe, laid out in spacetime like moments of a film. The flow of time, the sense that the present moment is special and the future is yet to exist, is an illusion created by the structure of our consciousness and memory. You remember the past because your neural patterns were established by past events. You don't remember the future because your neural patterns cannot be established by future events in this temporal direction. This conception of time is deeply unsettling. It suggests that the future already exists, that you have no free will to change it, that the sense of openness and possibility you feel about the future is merely subjective. Yet it is suggested by our best physical theories. The physicist John Wheeler proposed the delayed choice quantum eraser experiment, which suggests that the quantum state of past events can be influenced by measurements made in the future. This seeming reversal of causality, where future events affect past events, suggests that time may be even more strange and counterintuitive than even the block universe interpretation suggests. Quantum mechanics and the collapse of the wave function. In quantum mechanics, events are probabilistic until measured, at which point the wave function collapses to a definite outcome. This introduces a temporal asymmetry. Before measurement, the system is in a superposition of states; after measurement, it is in a definite state. The process of measurement appears to be irreversible in time. The collapse of the wave function, however, is itself mysterious and philosophically troubling. According to standard quantum mechanics, the wave function evolves deterministically according to the Schrödinger equation until a measurement is made. At that point, the wave function collapses discontinuously to one of the possible outcomes. But what counts as a measurement? Does consciousness play a role, as some interpretations suggest? Or does collapse occur whenever the system interacts with the environment? Alternative interpretations of quantum mechanics avoid wave function collapse. The many worlds interpretation, proposed by Hugh Everett, suggests that all possible outcomes of measurements actually occur, in different branches of reality. The deterministic evolution of the wave function describes the branching of the universe into parallel realities. In this interpretation, there is no collapse and no discontinuity. Reality is fundamentally deterministic, but it branches into multiple versions. The question of how to interpret quantum mechanics and what it tells us about the nature of time remains unresolved. Different interpretations carry different implications for time's nature and the possibility of free will. These interpretive questions lie at the heart of ongoing debates about what quantum mechanics tells us about physical reality. Time travel and causality violations. If time is not fundamental but merely a dimension of spacetime, is time travel possible? Einstein's general relativity permits some exotic solutions that could in principle allow closed time-like curves, paths through spacetime that return to their starting point in time. Rotating black holes might permit such curves. Certain configurations of exotic matter could theoretically warp spacetime to permit time travel. Yet time travel, particularly traveling backward in time, presents severe logical paradoxes. The most famous is the grandfather paradox. If you travel back in time and kill your grandfather before your parent was born, you would not have been born. But if you were not born, you could not have traveled back in time to kill your grandfather. This logical contradiction suggests that backward time travel leads to inconsistency. Some physicists, including Igor Novikov, have proposed that the laws of physics might conspire to prevent such contradictions. Perhaps causality is enforced by the laws of physics themselves. Any attempt to travel back in time would be prevented by some physical constraint. Alternatively, the many worlds interpretation might resolve the paradox. Traveling back in time would create a branch in reality in which your grandfather's timeline is altered, but you would exist in the original timeline where you were born. These considerations remain highly speculative. We have no evidence that time travel is possible, and powerful theoretical arguments suggest it may be forbidden by the laws of physics. Yet the possibility, permitted by general relativity, raises profound questions about causality, free will, and the nature of time itself. Part 8: Quantum Entanglement and the Interconnected Universe. The Spooky Action at a Distance. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper presenting what has become known as the EPR paradox. They argued that quantum mechanics was incomplete, that it did not provide a full description of physical reality. Their argument hinged on the phenomenon of quantum entanglement. Consider two particles created together, such that their properties are correlated. In quantum mechanics, if these particles have entangled properties, then neither particle has a definite property until measured. Measuring one particle instantaneously determines the property of the other, even if the particles are separated by vast distances. This seemed to violate the principle that no influence can travel faster than light, a cornerstone of relativity theory. Einstein famously derided this apparent action at a distance as spooky action at a distance. He argued that quantum mechanics must be incomplete, there must be hidden variables that determine the properties of particles from their creation, and quantum mechanics simply does not have access to these variables. The apparent correlation between distant particles would then be no more mysterious than the correlation between two gloves placed in separate boxes. Each glove determines the presence of the other, not through any action at a distance, but through a correlation established when they were paired. Bell's theorem and experimental confirmation. For 30 years, the EPR argument and hidden variable theories remained topics of theoretical debate. Then, in 1964, physicist John Bell published a theorem with profound implications. Bell showed that any hidden variable theory that reproduces the predictions of quantum mechanics must allow for faster-than-light influences, that is, must be non-local. More importantly, Bell derived an inequality that any local hidden variable theory must satisfy. This inequality, called Bell's inequality, could be tested experimentally. Experiments testing Bell's inequality, conducted by physicists including John Clauser, Stuart Friedman, Alain Aspect, and others, consistently showed violations of Bell's inequality. The results agreed with quantum mechanical predictions, not with local hidden variable theories. These experiments demonstrated that nature was non-local in a precise technical sense. The measurement of one entangled particle does influence the outcome at another entangled particle, even when they are separated by arbitrary distances. Yet these experiments do not permit faster-than-light communication. Although measuring one particle influences the probabilities for the other particle, an observer measuring the second particle cannot determine what measurement was made on the first particle. The results appear random from the second observer's perspective. The correlations only become apparent when the results from both measurements are compared. This represents a remarkable feature of nature. Quantum mechanics permits correlations between distant events that violate Bell's inequalities, yet these correlations cannot be used for superluminal communication. It is as if nature has been carefully designed to preserve both the extraordinary predictions of quantum mechanics and the prohibition on faster-than-light signals. Quantum teleportation and quantum communication. The correlations established through quantum entanglement can be used for information transfer, even without faster-than-light communication. In 1993, physicists Charles Bennett, Gilles Brassard, and others proposed quantum teleportation, a process in which the quantum state of one particle can be transferred to another particle at a distance, provided that the two particles are entangled and classical information can be transmitted between them. The protocol works as follows. One has an entangled pair and a particle whose state one wishes to teleport. By making a measurement that entangles the particle to be teleported with one member of the entangled pair, one obtains a measurement result. This result, sent classically to a distant location, allows a measurement to be made on the other member of the entangled pair that produces a particle with the desired quantum state. Although the teleportation process uses classical communication and thus cannot exceed the speed of light, the quantum state of the particle has effectively been transferred. Quantum teleportation has been demonstrated experimentally across increasingly large distances. In 2022, researchers achieved quantum teleportation over fiber optics spanning more than 45 kilometers. Such experiments demonstrate the practical power of entanglement and suggest possibilities for quantum communication networks and quantum computing systems. Quantum entanglement and information. The relationship between quantum entanglement and information has become increasingly clear. Entanglement represents a resource that allows tasks impossible in classical physics. Quantum computers can solve certain problems exponentially faster than classical computers. Quantum cryptography can provide theoretically unbreakable encryption. Quantum teleportation can transfer quantum states. Yet entanglement also suggests something profound about the nature of information. In classical physics, information is localized, it is stored in some physical system at some location. In quantum mechanics, entanglement suggests that information can be non-local, spread across multiple particles in a way that cannot be localized to individual particles. The physicist John Archibald Wheeler proposed that information might be fundamental to physics itself. In Wheeler's vision, the universe might be fundamentally informational, not made of matter and energy primarily, but made of information and the dynamics of information processing. Entanglement, from this perspective, represents an aspect of a deeper reality in which information transcends locality. The nature of the universe, interconnectedness and holism. The phenomenon of quantum entanglement raises profound questions about the nature of reality. The universe, according to quantum mechanics, is not composed of independent, localized objects. Rather, the universe is fundamentally interconnected. Particles that have interacted in the past remain entangled, retaining correlations regardless of the distance separating them. The entire universe, having been in contact since the Big Bang, might be in a state of universal entanglement. This vision of an interconnected, non-local universe contrasts sharply with the Newtonian view of a universe composed of independent particles interacting only through local forces. In the quantum view, the universe is woven together by entanglement at every scale. The physicist David Bohm proposed an interpretation of quantum mechanics in which particles are guided by a non-local quantum field. In Bohm's interpretation, particles are not truly independent, they are guided by an omnipresent quantum field that connects all particles throughout the universe. This interpretation gives substance to the intuition that the universe is fundamentally interconnected. These ideas have influenced philosophy and spirituality far beyond physics. Some have suggested that quantum entanglement supports philosophical holism, the view that reality is fundamentally a unified whole rather than a collection of independent parts. Others have drawn parallels between quantum non-locality and concepts from Eastern philosophy emphasizing interconnectedness. While such interpretations should be approached carefully, avoiding conflation of metaphorical truths with physical ones, they suggest that quantum mechanics touches on deep truths about the nature of interconnection and unity in reality. Part 9. The Multiverse and the Fabric of Reality. Beyond our observable universe. Modern cosmology raises a possibility that earlier generations of scientists would have dismissed as pure speculation. The universe we observe might be merely one universe among an infinite multitude of universes, a multiverse. This radical idea has arisen from multiple independent lines of theoretical reasoning and observational evidence. The inflationary cosmology proposed by Alan Guth, and refined by physicists including André Linde, suggests that the Big Bang did not occur merely once, but continuously. Inflation, according to some versions of the theory, never truly ends everywhere. Rather, some regions of spacetime cease inflating and form bubble universes like ours, while inflation continues eternally in other regions. Each bubble universe would have its own physical properties, its own fundamental constants, perhaps even its own physical laws. If this eternal inflation model is correct, then our Big Bang was not the beginning of all existence but merely the initiation of inflation in a small region of an infinitely larger inflationary space. Our universe is one bubble among an infinite number of bubble universes, each with its own properties, its own physical laws, its own history. The string theory landscape. String theory, a theoretical framework attempting to unify gravity and quantum mechanics, has suggested another path to the multiverse. String theory posits that the fundamental constituents of reality are not point particles but tiny vibrating strings. These strings vibrate in a spacetime with extra dimensions beyond the 4, 3 of space and 1 of time, we perceive. The extra dimensions of string theory are curled up at scales too small to observe directly, but the shape of these extra dimensions determines the physical properties of our universe, the fundamental constants, the particle masses, the interaction strengths of forces. However, string theory permits an enormous number of possible configurations of these extra dimensions. Estimates suggest 10 to the power of 500 or even more possibilities. Each possible configuration would correspond to a different universe with different physical properties. This vast collection of possible universes is called the string theory landscape. If the string theory landscape is real, then our universe, with its particular set of physical constants and laws, is merely one possibility among an incomprehensible multitude. And if eternal inflation creates bubble universes with different configurations of the extra dimensions, then all of these possibilities would be realized somewhere in the multiverse. The anthropic principle and fine-tuning. The existence of the multiverse, combined with the anthropic principle, provides a potential resolution to the mystery of cosmic fine-tuning. As noted earlier, numerous fundamental constants appear precisely calibrated to allow for life and complexity. The gravitational constant, the strength of the strong and weak nuclear forces, the density of dark energy, these and other parameters appear fine-tuned to remarkable precision. One interpretation of this fine-tuning is that a designer, a divine being, an advanced civilization, deliberately arranged the physical constants to permit life. An alternative interpretation invokes the anthropic principle. We necessarily observe a universe with physical constants compatible with life because we could not observe a universe incompatible with life. The multiverse provides a framework to make this argument precise. If universes with different physical constants are realized in the multiverse, then observers will necessarily find themselves in one of the rare universes with physical constants permitting life. The apparent fine-tuning requires no explanation beyond anthropic selection. This reasoning has proved controversial. Critics argue that the multiverse hypothesis is unfalsifiable. There is no way to test whether other universes exist, and thus is not science but metaphysics. Proponents argue that the multiverse is a consequence of our best current theories and must be taken seriously even if direct experimental confirmation seems impossible. Quantum many worlds and the branching multiverse. Yet another interpretation of quantum mechanics suggests another form of multiverse. The many worlds interpretation, proposed by Hugh Everett, suggests that all possible outcomes of quantum measurements actually occur. When a quantum system with multiple possible measurement outcomes is observed, the universe branches into multiple versions, each corresponding to one of the possible outcomes. In this interpretation, when you measure an electron spin and find it pointing up, the universe branches. In one branch, you observe spin up and continue with that knowledge. In another branch, equally real, you observe spin down. Both branches are equally real, you merely have access to one of them. This interpretation suggests a multiverse of continuously branching universes, exponentially multiplying with each quantum measurement. The multiverse is not something distant and inaccessible, but rather branching off around us at every moment. Every quantum event creates a branch, leading to an incomprehensibly vast array of parallel universes embodying all possible outcomes of quantum events. The philosophical implications are profound. In the many worlds interpretation, all possibilities are realized. You live in a branch where you read this article. But there are branches where you never found it, branches where you were born in different places, branches where you never existed at all. Your decisions do not eliminate possibilities, they merely determine which branch you traverse. Philosophical implications of the multiverse. The possibility of a multiverse raises profound philosophical questions about uniqueness, probability, and the foundations of scientific explanation. First, the multiverse challenges the notion that the universe is unique. If infinite universes exist, each with its own properties, then our universe is not special, merely one instantiation among many. This represents a continuation of the historical trend in which successive scientific revolutions have dislodged humanity from a supposed special place. Copernicus showed that Earth is not at the center of the solar system. Hubble showed that our galaxy is not central in the universe. Now the multiverse would show that our universe is not unique. Second, the multiverse changes the nature of probability and scientific explanation. In classical physics, probabilities describe our ignorance of underlying deterministic systems. If we knew the initial conditions and forces exactly, we could predict outcomes with certainty. In quantum mechanics, probabilities appear fundamental, outcomes are genuinely probabilistic. But in a multiverse where all possible outcomes are realized, probability takes on a different meaning. The question is not whether a particular outcome occurs, it does, in some branch or universe. Rather, the question is what fraction of branches or universes exhibit a particular outcome. This suggests a radical reconceptualization of probability from the frequency of outcomes to the measure of branches in a multiverse. Third, the multiverse raises concerns about whether physics has overstepped the bounds of scientific inquiry. Science has traditionally concerned itself with propositions that are in principle testable, that is, propositions about which evidence could be gathered. A universe beyond our observable region, or a parallel universe branching from our own, is by definition inaccessible to observation. How can we verify or falsify claims about these universes? Some scientists and philosophers have argued that if the multiverse emerges necessarily from our best theories, inflation, string theory, quantum mechanics, then we should take it seriously even if we cannot directly test it. Others have argued that such claims stretch the concept of science too far, venturing into metaphysics under the guise of physics. These debates reflect a fundamental tension in modern theoretical physics. Our best theories make predictions that seem to require the existence of unobservable entities, dark matter, dark energy, the multiverse. We can either limit ourselves to observable phenomena and abandon our most promising theoretical frameworks, or we can extend our conception of science to include these unobservable entities, running the risk of leaving the domain of empirically testable knowledge. Part 10, Philosophical Synthesis and the Question of Ultimate Reality. The Limits of Human Knowledge. Our exploration of cosmic mysteries, from the invisible dark matter and dark energy that dominate the universe to the singularities where physical theories break down, from the quantum correlations that link the universe non-locally to the possible multitudes of universes beyond our perception, brings us to a profound realization. There exist fundamental limits to human knowledge and understanding. The physicist and philosopher Karl Popper articulated a principle of demarcation between science and non-science. A theory is scientific if it is in principle falsifiable. Yet we have encountered numerous phenomena that approach or exceed the boundary of falsifiability. Dark matter manifests only through gravitational effects, we have no independent way to verify its existence. Dark energy is inferred from the accelerating expansion of the universe, we possess no other method to detect it. The multiverse, by definition, lies beyond our causal connection to our own universe. These examples do not indicate failures of science but rather the ultimate frontiers of scientific inquiry. They mark the boundaries where human knowledge runs against fundamental obstacles imposed by the structure of the universe and the limits of human perception and understanding. The universe is vaster than we can comprehend. 1 billion light-years is to the universe as a single grain of sand is to all the beaches of Earth, an insufficiently small fraction to convey the proportion. Time scales in cosmology are equally daunting. 1 billion years is a mere instant in the universe's history, yet it is vastly longer than human civilization has existed. The human mind, evolved on the African savanna to navigate a world of kilometers and decades, struggles to grasp these cosmic scales. Being and nothingness, existence and reality. The ultimate mysteries of the universe point toward perhaps the deepest philosophical question: why is there something rather than nothing? This question was posed by philosophers including Heidegger and Leibniz, and it remains unanswered by science. The laws of physics describe how the universe behaves given initial conditions, but they do not explain why the universe exists at all, or why these particular laws govern it rather than some other set of laws. Some physicists argue that quantum mechanics provides an answer. In quantum field theory, virtual particles spontaneously pop in and out of existence in the vacuum. Perhaps the universe itself is the ultimate quantum fluctuation, a vast, structured fluctuation in the quantum vacuum field that happened to be permitted by the laws of quantum mechanics. Yet this explanation simply relocates the question: why do these quantum laws exist? Why does a quantum vacuum exist? We could posit that the laws of physics are necessary and could not be otherwise, but this remains a metaphysical assertion unsupported by empirical evidence. Others suggest that the question itself is misconceived. Perhaps nothing is unstable or meaningless. Perhaps existence is more natural than non-existence. Perhaps the question presupposes that non-existence is the default state, whereas actually existence is inevitable. These considerations move us beyond science into pure philosophy, metaphysics in the classical sense. Science cannot answer the question of why there is something rather than nothing. It can only describe the nature of the something that does exist. The evolution of wonder. Humanity's relationship with the cosmic mysteries has evolved dramatically. For most of human history, the mysteries of the heavens were addressed through mythology and theology. The stars were divine, the heavens were the realm of God, and the origins of the universe lay beyond human comprehension and investigation. The scientific revolution, beginning with figures like Copernicus, Galileo, and Newton, made the cosmos subject to rational investigation. Mystery became an invitation to inquiry. Previously inexplicable phenomena were revealed to obey mathematical laws. The heavens became subject to the same laws as the earth. Yet as science has advanced, we have encountered mysteries anew. Dark matter and dark energy constitute 95% of the universe's content, yet remain mysterious. The fundamental laws of physics at extreme conditions, near the Big Bang, in black hole interiors, at Planck scales, remain unknown. Consciousness, despite neuroscience's progress, remains fundamentally mysterious. Life's origin in a non-living cosmos still eludes explanation. These modern mysteries differ from pre-scientific mysteries. They are not religious mysteries appealing to divine will, but scientific mysteries embedded in the structure of physical reality. Yet they indicate that reality is far richer, far stranger, and far less comprehensible than our common-sense intuitions suggest. The cosmic perspective. The astronomer Carl Sagan wrote about the cosmic perspective, the shift in worldview that occurs when we contemplate our place in the universe. When viewed from the vantage point of space, the Earth appears as a pale blue dot, a fragile sphere of life suspended in the void. National borders, political conflicts, religious differences, all appear insignificant when viewed from this cosmic perspective. The cosmic mysteries we have explored in this essay foster a similar perspective. We are conscious beings arising in a universe we do not fully understand, governed by physical laws whose ultimate origin and nature remain mysterious. We have managed to decode many of these laws and to understand vast reaches of cosmic history. Yet at every frontier of understanding, we encounter new mysteries. This should inspire not despair but humility and wonder. Humility, in recognizing that despite our scientific achievements, the universe transcends our understanding. Wonder, in recognizing that the universe remains inexhaustibly strange and beautiful. The physicist Richard Feynman expressed this sentiment: "I would rather have questions that can't be answered than answers that can't be questioned." The persistent mysteries of the universe are precisely this, questions that drive scientific inquiry, that demand new theories, new experiments, new ways of thinking. The future of cosmic inquiry. What does the future hold for the investigation of cosmic mysteries? Several frontiers seem particularly promising. First, the detection and study of dark matter remains a high priority. New experiments under construction, XENON and Super CDMS, ADMX, continue the search for dark matter particles. These experiments might finally reveal the nature of the substance comprising 85% of the matter in the universe. Second, advancing observations of the early universe through next-generation telescopes promise to refine our understanding of cosmic history. The James Webb Space Telescope, launched in 2021, has already begun to reveal galaxies formed in the early universe. Future telescopes will probe even earlier epochs, potentially addressing questions about galaxy formation and the first stars. Third, Advances in gravitational wave astronomy open a new window onto the universe. The Laser Interferometer Gravitational Wave Observatory, LIGO, and other gravitational wave detectors have begun detecting ripples in spacetime created by merging black holes and neutron stars. These observations provide unprecedented data about extreme physics near black holes and neutron stars. Fourth, progress toward a quantum theory of gravity, whether through string theory, loop quantum gravity, or other approaches, could reveal the nature of spacetime at Planck scales and illuminate the physics of the Big Bang singularity. Finally, continued investigation of consciousness and the neural correlates of subjective experience may eventually provide insights into how physical processes give rise to conscious awareness, or alternatively, may reveal new fundamental principles underlying consciousness. The eternal mystery. Yet despite all these advances, it is likely that mysteries will remain. For each mystery solved, new puzzles emerge. The universe is not merely vast and complex, it appears to be inexhaustibly mysterious. This is not a limitation of the human mind, though our minds do have limitations. Rather, it seems to be a feature of reality itself, that the universe is structured in such a way that understanding deepens but does not end. The physicist and philosopher Bertrand Russell described a similar situation in his discussion of the limits of philosophy. Is there any knowledge in the world so certain that no reasonable man could doubt it? Russell concluded that many of our deepest questions resist definitive answers. We can progress in understanding, we can clarify the questions, we can rule out certain answers, but we may never achieve complete certainty about the ultimate nature of reality. This does not diminish the value of inquiry. Rather, it ennobles it. The pursuit of understanding in the face of irreducible mystery, the attempt to make sense of cosmos that transcends sense, the endeavor to extend human knowledge toward the asymptotic limits of knowability, these represent the highest expressions of human intellectual aspiration. Conclusion: the universe as mirror. The cosmic mysteries we have explored, the invisible dark matter and dark energy, the extreme physics near black holes, the quantum phenomena connecting distant regions non-locally, the possible multitudes of universes, the emergence of consciousness in an apparently physical cosmos, these mysteries serve as a mirror in which humanity sees itself reflected. We are creatures of the universe attempting to understand the universe. We are portions of matter and energy that have organized themselves into structures complex enough to contemplate the whole. We are the universe becoming aware of itself, however briefly, however incompletely, however fallibly. The mysteries of the cosmos are not external puzzles to be solved. They are intrinsic to existence itself, intrinsic to our nature as conscious observers existing within physical reality. In our attempt to understand the universe, we are ultimately asking, what are we? What is consciousness? What is reality? What is possible? The honest answer is that we do not know. We have theories, we have observations, we have mathematical models of stunning power and explanatory reach. Yet they remain incomplete. Mysteries persist. The universe retains the capacity to surprise us, to challenge our assumptions, to reveal aspects of reality that our theories did not predict. This is the gift that cosmic mysteries offer, not answers, but the endless possibility of deeper understanding. Not certainty, but the continuing adventure of inquiry. Not a universe that can be captured in formulas and filed away in human knowledge, but a cosmos that transcends all our categories and invites eternal wonder. As we look upward on a clear night, at the stars winking like distant thoughts in the cosmic mind, we touch something profound. We participate in the universe's self-awareness. We ask questions whose answers extend beyond our comprehension yet toward which all human understanding reaches. The mysteries of the universe are not defects in our knowledge. They are the depths of reality itself, calling us to deeper thought, richer imagination, and more profound humility before the inexhaustible cosmos in which we live. Epilogue: the human response to cosmic mystery. Humanity has always stood at the threshold of mystery. For our ancestors, the night sky represented an unknowable realm of wonder and terror. The stars were gods, or the homes of gods, or messages from the divine. Civilizations constructed elaborate mythologies to account for the celestial dance they observed, finding meaning in the heavens. The scientific age brought new understanding, but it did not eliminate mystery. Rather, it transformed mystery. We moved from myths of gods and cosmic serpents to theories of gravity, quantum mechanics, and expanding spacetime. We exchanged the comfort of familiar stories for the austerity of mathematical description. Yet the sense of wonder, the recognition that reality transcends our understanding, remains. This transformation represents progress. We have genuine knowledge now. We can predict eclipses centuries in advance. We can calculate the trajectory of spacecraft traveling to the outer planets. We can determine the age of the universe and trace its history back toward the Big Bang. We have decoded the radiation signature of the universe's infancy. These accomplishments are extraordinary. Yet they come with a cost. The cost is the loss of certainty, the recognition that the more we understand, the larger the realm of mystery becomes. In science, each answer spawns new questions. The cosmos becomes more mysterious the more deeply we understand it, not less. Perhaps this is as it should be. A universe fully comprehensible to human minds would be a small universe, a limited universe, a universe that fit within the boundaries of human categories. The universe we actually inhabit resists all attempts to cage it in human concepts. It constantly escapes our grasp, reveals new aspects we did not anticipate, presents us with phenomena that overturn our assumptions. In this resistance, in this inexhaustibility of cosmic mystery, humanity encounters something that transcends both science and religion, though it touches both. We encounter the genuine other, reality that is not created by human thought, not contained by human language, not exhausted by human categories. The response to cosmic mystery can be several things. It can be awe, a direct emotional apprehension of the vastness and strangeness of reality. It can be humility, a recognition of the limits of human understanding and the smallness of human perspective. It can be curiosity, an impulse to investigate, to probe deeper, to ask further questions. It can be beauty, an appreciation of the elegance of natural laws and the harmony underlying cosmic structures. And it can be meaning, a sense that in contemplating the cosmos, in attempting to understand our place within it, we are engaged in something significant, something that matters. All of these responses are valid. The great scientists throughout history have been motivated by various combinations of these. They have been awestruck by the beauty of natural laws. They have been humbled by the vast scales of the cosmos. They have been driven by curiosity that could not be satisfied until new knowledge was attained. They have found meaning in the attempt to understand the universe and humanity's place within it. The cosmic mysteries explored in this essay represent the living frontier of human understanding. They are not mere intellectual puzzles but profound aspects of reality that resist simple explanation. They are gateways to deeper thought, invitations to contemplate what we are and what the universe is. As we face these mysteries, we should do so with appropriate intellectual modesty, recognizing that we may be near the boundary of human understanding in many domains. Yet we should continue to push against these boundaries, to ask deeper questions, to develop new theories, to seek new evidence. For in this ongoing conversation between the human mind and the cosmic other, in this continuing attempt to understand our place in an extraordinary universe, we are realizing the highest possibilities of human consciousness. The universe remains mysterious. May it remain so for all future ages. For in mystery lies the possibility of continued growth, continued wonder, and continued meaning-making. The cosmic mysteries are the universe's gift to conscious observers, an inexhaustible resource for thought, reflection, and continued inquiry. This is where we stand, on a planet orbiting an ordinary star in an ordinary galaxy, contemplating mysteries that stretch to the edge of cognition. We are creatures of dust who have learned to study the stars. We are part of the universe attempting to understand the universe. And in that attempt, we discover what we truly are, not passive observers of a fixed cosmos, but active participants in the universe's continuing evolution toward greater complexity, greater understanding, and greater awareness. The mystery persists. And in its persistence lies our hope.